Good morning, all of you. Today we start our lecture on portfolio credit risk. We have just in the last sessions we discussed about different aspects of individual credit risk from individual loans, and we have gone through the different parameters which we need to arrive at the expected loss from those loans. Basically, we discussed about the probability of default, loss given default, and the exposure at default. But sometimes in some cases we just gave different names for those similar type of things. Now, probability of default sometimes referred to as expected default frequency. Now, this expected default frequency is a particular parameter which is not completely similar to the probability of default, but EDF is when we base on certain data. There we have to arrive at EDF. Now, EDF, if you get the EDF for a very longer period, the average EDF can be taken as the probability of default. That is the connection. Now, if you say the other one, exposure at default, and it is sometimes we refer to as average exposure. Now, in a revolving type of an advance, this average exposure is little difficult to arrive at. But when you go to the normal loan, the exposure at default or the average exposure would be the outstanding balance. Now, when you go to the loss given default, that is the particular loss which we have to incur if there's a default. Then we need to go for some recovery action, and through the recovery action, we might recover a percentage of the particular outstanding amount. So that is what you call the recovery rate. If you take 1 minus recovery rate, so that is what you call the loss given default. In the case of an individual loan or individual credit facility, what we do is we can estimate the expected loss of such a loan by multiplying the probability of default, loss given default, and the exposure at default. And it can be multiplied with the maturity also. But what happens is, that is the expected loss. Now, in certain cases, there can be unexpected losses also. Even in individual form, you need to understand the way in which we can arrive at the unexpected loss. So even though it's a probabilistic figure, estimating that unexpected loss also will be beneficial for the bank, because when a bank deals with its portfolio, the bank has to estimate not only the expected loss, but the unexpected loss also. Because in capital formation, assignment of capital depends on not only the expected loss, but the unexpected loss also. Therefore, for a bank, it is very much important to arrive at the unexpected loss. But the issue here is, there can be several mathematical and statistical notions where we have to go through when we arrive at unexpected loss. And I think last time we discussed about the nature of unexpected loss and how it vary with PD, LGD or loss given default and the exposure at default. In the case of expected loss, it varies with PD, LGD and what is the one, exposure at default. It's an increasing function and it's a linear function. So expected loss is a linear function. So then we can just explain it or demonstrate it as a straight line. But if you go to the unexpected loss, it also will increase with PD, LGD and the EAD. But that particular increase is an exponential increase. So I just show you some graphs also in order to show that. The criticality of these things really came up with that characteristics. That is why a bank has to be more careful in their calculation of unexpected losses. Because if you can follow a better methodology to arrive at unexpected losses, that could help the bank to manage their risk in a proper way. Right. We will go to the presentation. Right. The things which I have already explained, I will just show you. Yes. Now the graph. The set graph is this. Because what I want to tell you is we should not unwarrantedly deal with only the numbers, because that will become a very routinized exercise. So then whatever you do, whatever the calculation you do, you have to do it in a very understandable manner, because you need to get the concepts understood. If you do not understand the concepts, there's no use of doing calculations. But altogether, you need to see why we do this calculation, what is the real implication, what type of estimation we are going to do, and what type of assumptions we have made in order to do the particular calculation. If you do not know that, merely doing calculation will not help. Even sometimes, you need not to do any complicated calculations. But if you know the concepts clear, even sometimes you can have a very simpler type of a calculation to arrive at the same thing. So that is what you need to understand. Now just look at this graph. This graph is constructed on the basis of, now you can see, along the x-axis, the EDF is taken. That is expected default frequency. It is a proxy for PD. Then the other one, in the vertical axis, you have percentage loss per unit of AE. Percentage loss per unit of AE. Now, what does that mean? Percentage loss per unit of AE. Now, AE is the average exposure. For unit of AE, so one unit of average exposure, what is the percentage loss? That is what it means. So that means if you want to get the real loss, the percentage loss has to be multiplied with exposure. That is what it means. However, now it gives a certain indication of loss. Now, just look at the expected loss curve. It's a clear straight line. So that really gives us the understanding. That really shows us that EDF and percentage loss per unit of AE has a relationship, and it's a linear relationship. It's a linear relationship. And at the same time, you can see the line, the gradient of the line is moderate. It gradually increasing. The particular line, the gradient of the line, you can see, it's a gradual type of a increment. But if you go to the unexpected loss curve, there you find that the unexpected loss, it increases exponentially. When you have a small increase in EDF, you have a very big increase in the loss, percentage loss. Now, that shows the behavior of unexpected loss versus EDF, or EDF, when EDF changes or when EDF increases, how the unexpected loss increasing. So that is the criticality here. So therefore, the EDF, if there's a small increase in EDF, that would result in a very high increase in unexpected loss. So that is a very important point to note. So then we need to go to the calculations. Now you just look at these factors, and when you increase different factors, which we want to go through, and how the expected loss and unexpected loss behave. Now, just look at the first thing, that is the recovery rate, increase in factors. When recovery rate increases, what will happen to the expected loss? It will decrease. Unexpected loss also will decrease. So then, as a target or as an objective, a portfolio manager or a credit manager should try his best to increase the recovery rate. So when increase in recovery rate, what will happen? The expected loss will go down, as well unexpected loss also will go down. Then when you go to the credit quality, what do you mean by credit quality? Credit quality is you are having a high recovery rate. Not only that, your NPE is very, very low. So that is what you mean by credit quality. Not only that, every loan in the portfolio have a very low probability of default. So that means all the loans are in a better form. And expected loss will decrease if you increase the credit quality. Expected loss will decrease, unexpected loss also will decrease. Then if you take the other one, expected default frequency, that is a proxy for PD, and when it increases, what will happen? The expected loss will increase, unexpected loss also will increase, but when you compare these two, unexpected loss will have a very exponential increase. This is the most important factor you need to note. So I think you can make a note on this. You can say, with a very minute change in expected default frequency, very minute increase in expected default frequency, there would be an exponential increase in unexpected loss. So this is the factor we need to understand. Because in all credit risk management operations, any person who engages in credit risk management, he should keep in mind that this factor, because the probability of default, even it's a very small increase, but the increase of unexpected loss will be exponential. Now that is why we are very much careful with regard to the migrations. What do you mean by a migration? Adverse migration is your credit rating is converted or changed to a adverse rating or inferior type of a rating. For example, say when you grant an advance, the particular borrower, the counterparty, the rating was AAA. But say after 6 months or 8 months, you get the publication or you get the real notice that the particular counterparty has been downgraded by the rating agencies to the next notch, that is AA plus. But it's a very minute change in the PD. But you have to be careful because it could increase the unexpected loss at a substantial amount. So this is the thing which you need to understand. So therefore, when you deal with especially the high volume type of advances, you have to be very careful about the rating migrations because it really increases the unexpected loss in an exponential manner. Now, sometimes people disregard that type of adverse migration to one notch. Then we can go to the calculations. Actually, we did that. The portfolio expected loss calculations and all. Last time also we discussed about this. Then the unexpected loss. Now we just had a glance on this last time. The calculation of the portfolio unexpected loss is more complicated from the cross terms in the variance formula for N asset portfolio. Now it is like this. Now when you have, as we just discussed, this is the important formula for individual loans unexpected loss, UL1. So it is, the formula is given as AE1 into square root of EDF1 into sigma squared of LGD1 plus LGD1 squared into sigma squared of EDF. So then the particular codes being explained as adjusted exposure AE, EDF as expected default frequency, LGD as loss given default of asset 1, and the standard deviation as sigma. Now, I think we discussed about this diversifiable and undiversifiable risk and the effect of correlation. The correlation actually we refer to the correlation of default. Intuitively, as the correlation between assets increases, the bank suffers from concentration risk. I think last time we discussed about the measures of concentration risk also. And the limitations of correlations. Now just look at this, because we have to have some idea about this. Because when you grant credit, we should have a basic understanding on the correlations. When defaults are not normally distributed, the zero correlation does not imply defaults are independent. So this is one factor. Now, if defaults are not normally distributed, now that is not a, I don't know, people don't realize what it is. Now, in most of the cases, we assume that the particular parameters what we are trying to survey or what we are trying to test normally distributed. So that's the normal assumption. But in some cases, it may not be normally distributed. Now, in a normal distribution, there can be several characteristics. Now, when you go for a very high number of advances in a portfolio, then in most of the cases, the PDs are normally distributed because the number is high. Especially that number has to be more than 30. There's no hard and fast rule to say that, but there's just a convention that if it is more than 30, say, for example, if you have a portfolio which has more than 30 loans, I think we can just take it as a approximately normally distributed line. But if you have 100 or 100, more than 100 type of advances in one portfolio, invariably you can say it's a normally distributed defaults would be there. So if it is normally distributed, then the implication is if there's no correlation, then we can say the defaults are independent. What do you mean by that? One loan's default would not affect the other loan's default. So that is what you call defaults are independent. Now I think you can find out several examples for this. You all know that in some cases, in some advances becoming default, then it might really affect some other advances becoming default. So we call it a contagion effect. I think you might have come across that that type of situation in your own organization. But when you go to the measure of correlation, so these are the issues which we have to face with. The correlation is not a good measure of dependence when the underlying variables have distributions that are with infinite variance. So if the variances are very high, the correlation could not be a good measure. Now, in order to overcome this, there's a particular thing that has been innovated. We call it a copula. Now, it's a multivariate distribution function, and it really mitigated all the effects in the correlation, the bad effects. So now, irrespective of the assumptions, now assumption is now basically we have to assume that all the defaults are distributed in a normal distribution. So even without that assumption also, the copula will help us to do the evaluations. And we call that a particular model there's a model called Gaussian copula model, and that is what we normally use to arrive at this unexpected loss. Now just look at it. Unexpected loss of a portfolio can be estimated by quantifying the unexpected loss of each asset and arriving at the joint probability distribution. Now let the unexpected loss of each asset of the portfolio is given by following relationship. Now that relationship is UI is equal to UI is the unexpected loss is equal to AIF. AI is the correlation between two assets. F is the common systematic risk factor. Systematic risk is the market risk. Then the square root of 1 minus AI squared. AI is the correlation. ZI is the idiosyncratic factor for ith asset. Now, what do you mean by idiosyncratic? Idiosyncratic is the inherent type of a risk in a company or in a particular counterparty. It provides an easily implemented way to derive the default PDF of a portfolio given the correlation between assets and the expected default rate EDR. Right. Now, before going into this, we will see how we can go into a individual assets or individual loans unexpected loss. Now, this is the formula for that. If you take an individual loan, UL1, so loan number 1, then its unexpected loss is calculated with this formula. So we can go through a certain example to have a good idea about it. Right, there's a small example now, because you can make use of this formula to calculate that. I will just show you. Right. Now look at the board. Do loans A and B have following characteristics? Now assume that these two loans are in one portfolio. ULA, that is the unexpected loss of A, is 20 million. Unexpected loss of B is 30 million. And the correlation between these two loans is for minus 0.67. Minus 0.67. Now, by applying the formula, you need to calculate the portfolio unexpected loss. Since there are two loans in the portfolio, there's a formula for the calculation of that. So just do it with the numbering, because then you can get some idea what you are going to do. Now I am just taking only two loans because this is the most simple case for a portfolio. But if you have more than two loans, then it will be a little difficult. But this is the simplest form of a portfolio. So then, in order to just have some type of an familiarity, you just calculate this and see what is the answer. You can apply the formula. You can apply this formula. Yes, you can see the formula, no? This is the formula you have to use. ULP is equal to square root of UL1 squared plus UL2 squared plus 2 rho 1 to UL1 into UL2. So just do it. Yes, I think this is not a big task, but in order to have some practice, you can do this. Yes, anyone who did the try to do it. You have to just apply the formula. ULP is equal to square root of UL1 squared plus UL2 squared plus 2 rho 1 to UL1 UL2, the square root. Yes, Suresha. Just try to do the
So
calculation.
36.03.
36.03. Now, you did, what you have you just did it this way? 20 million now, that is 20 squared. You have to get 20 squared.
And 30 square.
20 squared plus 30 squared.
Right. So there's a
Plus,
calculation.
then it has to be minus, because that row AB is minus 0.67. So then,
right, okay.
Then minus 0.67 into 20 into 30 into 2.
Into 2.
Then you get that value as 496. The result as 496, but you have to take the square root of that. Have you got 496 for that?
Sir, I not put this minus 0.6. I have put 0.6.
Right. That's the issue. Right. Anyway, now it is minus. It is minus. So then you have to apply minus, and then in the 2 into row 1, 2, and that particular statement comes as minus.
Yes.
Then you get 496 as the result. Then you have to get the square root of that.
Right.
You have to get the square root of that. When you get the square root, you get this answer, 22.27. That is the answer. Now, how about the others? Now, have you just tried it? Have you tried it? Yes, Suresha? If anyone wants it on the board explanation? If not, I can go to another one, another example. What do you say?
So, if possible, you can please explain.
Okay. Right. Now you get this is only the application of a formula, right? I will just put the formula down. Then you say ULP, that is the portfolio unexpected loss, is equal to square root of. Now here you have ULA squared plus ULB squared plus 2 rho AB ULA ULB. Now this is the formula. This is how the formula has to be applied. Now what we need to do is we need to substitute the values here. So then you get 20 squared plus 30 squared plus, now here it becomes minus because this row AB is a minus value, minus 0.67 minus 2 into 0.67 into 20 into 30. So this is the value ULP, is square root of this. Now when you calculate it, this will become 400, this will become 900, and with that you get the answer as ULP is equal to square root of 496, and the answer is 22.27. That is in millions, right? This is the unexpected loss for the portfolio. Now just look at it. Now, can we get the portfolio risk as 50? Because now someone can argue, when you have 2 loans in a portfolio, one loan has an unexpected loss of 20, The other loan has an unexpected loss of 30. Now, when you want to get the total unexpected loss for the portfolio, but unlike in expected loss, now if you have expected loss in this manner, we could have added it up. Then the portfolio expected loss is the addition of two loans, individual losses. But in this case, since it is the unexpected loss, you can't do that. If you have done that, then the answer would be 50, is it? But we now know with the formula, answer is only 22 point something. That is little higher than one loan. Why it is so? I should get an answer from you. Now, what the portfolio risk is so low? Because it contains two loans of 20 and 30. But if you take the both loans, the losses become lower, like it's only 22 point something. With the loan of 30, it added only 2 point something. So why it is so? This is a very important question. So you just think over it and answer that question. Yes.
Because the correlation is negative.
Yeah, very good. Since the correlation is negative, the portfolio unexpected loss has come down to a greater extent. So therefore, if you can form a portfolio with the loans having negative correlations, then you can bring down your risk to a very, very great extent, especially the unexpected loss. But you need to be careful when you grant advances, when you originate advances, then you need to see whether these advances will have negative correlations. Because that, of course, you can observe. You can observe the characteristics of those advances or the counterparties. Then it would become negative correlation, negative correlated. Because of that, the portfolio risk or the portfolio unexpected loss will become lower. Right. Now this is we have already discussed the very, very say simple type of a portfolio. But the portfolio can have 3 loans, 4 loans, 5 loans, and so on and so forth. So if that is the case, we'll try to see what will happen. If you know the unexpected losses of each loan, and if you have the correlations also, correlation coefficient also, then you will be in a position to calculate the portfolio risk. Now we will go to 3-asset portfolio. We will go to a 3-asset portfolio. No, I just want to show you in the case of a portfolio with a very high number of assets, what are we going to do? So for that, we need to have these things clear, right? Now, shall we go for a 3-asset portfolio and get the things calculated? So in order to do that, you need to have another formula to be familiar with. I will just put that formula on. Portfolio with 3 loans. So we can say A, B, and C. Right? Then what is the portfolio risk, unexpected loss? The square root of ULA squared plus ULB squared plus ULC squared plus 2 rho AB ULA ULB plus 2 rho BC ULB ULC plus 2 rho AC ULA ULC. So this is the formula. So just look at it. Now there's a particular pattern. You should understand that pattern. Now just look at the first three terms. Those three terms are square terms. Since you have A, B, and C, unexpected loss of A, unexpected loss of B, unexpected loss of C to be taken into consideration. And the first three terms are ULA squared plus ULB squared plus ULC squared. Then you start with the correlation terms. Now, since you have ABC, how the correlations will become possible? Now, since A, B, C are there, you have a correlation with A and B. You can expect a correlation between B and C. And you have to expect another correlation between A and C. So then there will be three correlations. Now, always the correlation comes only with two assets, two loans. But since there are three loans, there can be several correlations. When there are three assets in a portfolio, there will be three correlations. Now, if you put it in English letters like AB, BC, CA, that's all. Then the formula is written as first three terms are square terms. Then you start with 2 rho AB, 2 rho AB into ULA into ULB. Then 2 rho BC, ULB, ULC. Then 2 rho CA or AC, ULA, ULC. Then you have to get the total and the particular result. You have to get that particular result square root. That will be the portfolio unexpected loss. You got it now? Right. Now, shall we do a example? Shall we do an example on that? Now, likewise, now this is three assets. But if you have four assets also, you will have the same type of a formula. Now, say for example, if you have four assets, how many correlations would be there? If you have four assets, how many correlations? I think we have discussed about this, even without doing this formulation, but we did some discussions on this. Tell me how many correlations can be seen or can be expected when you have four assets. If you want, you can write it down on a piece of paper and see. There you have A, B, C, and D. Yes, how many? Just do an exercise and see what is it. And if you want, you can write it down and see. Because cyclically you can have it. A, B, B, C, C, D. There are three. And not only that, you have C, A, D, A. So likewise, you can just see what are the number of say what is the number of correlations you can expect from that.
6 correlations.
How many?
6.
6. Yes, correct. 6 correlations are there. So you can namely give it. Now, in the same way, if you go for 5 asset portfolio, there also you will have another number of correlations. Can anyone tell me the formula to get that number? The correlation number. How many correlations are there? There will be a formula for that. Then it is easy for you to just do the calculation if you know that type of formula. Yes. Just to see that. Yes. Can anyone come up with a formula for that? That would be very helpful. Now, these are very practical type of things. Now, don't worry about this mathematics or whatever, but it's a practical thing. Now, say for example, if you have a portfolio, say housing loan portfolio, say you have 1,000 loans there, then how many correlations you will expect there? So that type of a thing, it is readily available now if you know this. Yes, can anyone tell me the formula for that? Yes, you have not given any messages here. Anyway, I'm just expecting messages from you with the formula. Now, even sometimes, if I ask this question, if there are 10 assets in the portfolio, how many correlations you can expect? If there are 10 assets. Yes. If there are 10 assets, how many correlations you can expect? Now, this is a thing which you can give.
45.
Yeah.
45.
For 10 assets, it would be 45. It would be 45. Correct. So then how you have got that answer? If you go for that, then you will be in a position to really get a formula for that.
By adding
Yeah. Adding
1 to 9.
Adding no.
I don't have the formula, sir, but by
Well,
adding.
you know how to do it. Anyway, now you gave the correct answer for 10 assets. You gave the correct answer. But no, what you have done to get that answer? Have you just written it and got it, or just did some mathematical thing? No, some arithmetical thing. if you go backward and see what you have done, then you will be in a position to just give the formula. Now, when you say 10, right? 10 into what you get? Or in other words, how did you arrive at 45?
I write the numbers and 1, 2, 3, 4, 5 up to
Yeah.
9.
Yeah. 9 or 10?
Oh, 9 up to 9.
Up to 9, yes. Then what did you do?
I add 1 plus 2 plus 3 plus 4 plus 5 plus 6.
Good. I mean, now that's that's another way. Anyway, now if you can just think about the formula to just show that or just depict that. I think what you have done was correct. It is correct, really correct. It is really correct, but the way you did it, you can put it in the formula. Now, what you did was you just add one. No, for everyone you add one. No, is that so? Yeah. So then,
In a big amount, it is not possible, sir. No?
no, even it is possible. I think no issue, because what you did was you add one and then divide it by 2. No, is that so? Right. So just give me the formula then. So just assume that you have n numbers, n simple n. That is a number. It can be anything, 1, 2, 3, 4, whatever it is. Then what will happen to n? Someone else can try. Charit, Uresha, you all can try. I think this Miss Tirukuma also tried, and she did a very good try. I think now these things are very important, because if you innovate like this, then it will be very good for you. Yes, Charit or Uresha?
So the standard formula is the total portfolio divided by the combination that we want minus 1. N divided by
n divided by
if our combination is 2, 2 into 5 n minus 1.
Very good. So I can just give the formula now, because n into n minus 1 divided by 2. N into n minus 1 divided by 2. I will put it on the board. N into n minus 1 divided by 2. Now we will just trial it for numbers, any number. So if the number is if the number is 1, what will happen? It will be 0. There's no correlation at all, because correlation means at least you need to have 2 assets. So if you have 2 assets, what will happen? 2 minus 1 is 1. 1 into 2. 1 into 2 divided by 2, that is 1. So when you have 2 assets, only one correlation is there. When you have 3 assets, 3 into 2 divided by 2, then 2 and 2 cancel, then 3. When you have 3 assets, there will be 3 correlations. When you have 4 assets, 4 into 3 divided by 2. So that means 6. When you have 4 assets, there will be 6 correlations. Even this Tirukuma has done the same thing, but she was not able to give the formula. Even if you have, say, 10 assets, 10 into 9 divided by 2. 10 into 9 is 90. 90 divided by 2 is 45. That is how the 45 came for 10 assets. Now, if you have 1000 assets, what will happen? 1000 assets. Yes, if you have 1000 assets, what will happen? What is the number of correlations you have? 1000 assets. Yes. what you should do? Just go, do the calculation and give me. Say, you have a portfolio with 1,000 assets. How many correlations will be there? How many correlations we can expect there? Yes.
Is 499,500?
499,500. Yes, correct. Now, what you need to do is n into n minus 1. N is 1,000, n minus 1 is 999. So that is 999,000 divided by 2. Then it will become 499,500. So that is the answer. Now you can see, when you have 1,000 assets, you will have 499,500 correlations. Now this is a very, very big amount comparing to the number of assets. So that is why the correlations will become a big nuisance for a portfolio. But only thing is, now out of these correlations, say more than half of the correlations are minus correlations, then the effect on the total risk of the portfolio would be very much favorable, because it will go for the reduction of the loss. But if these all correlations are positive correlations, then what will happen? The default or the losses would be very high. Losses go up with positive correlations. That is the issue. So therefore, only thing is, now you can get an idea how many correlations would be there in a portfolio with the number of portfolio loans. Right. Now I think that is enough for that. And I will just give you a small exercise to deal with, say, now this using this formula, because I will give the data of a portfolio which contains 3 loans. Right? ULA is equal to 10 million. ULB is equal to 20 million. ULC is equal to 15 million. Then I will give you the row. Row AB equals 0. Row BC equals 0.5. Row CA equals 0.6. Right. With that, calculate portfolio unexpected loss. Calculate the portfolio unexpected loss. Right, do that.
Sir, can you repeat the question, please?
Yes. ULA is equal to 10 million. ULA is the loss of a loan A. ULB is 20 million. ULC is 15 million. Row AB is 0. Row AB is 0. Row BC is 0.5. That is the correlation. Correlation between A and B 0. Correlation between B and C 0.5. 0.5. Correlation between C and A, 0.6. Calculate the portfolio unexpected loss. Now, I think you can make use of this formula. You can do that. It is a matter of applying the formula. I think all of you can try that. Now, just make sure that you get this familiarity. Now, you don't have any fear with the numbers. That is what I need to inculcate in your minds. You need to just forget about the fear for numbers. If you have that type of fear, it's a very dangerous thing for you, because as bankers, you should be in a position to swim in the numbers. So make sure that you have that ability. Yes, Suresha, you all can try that. And you will get some confidence also when you work out this type of sums. And you can see one correlation has become 0 also as per the data. And you can just see the effect of that. Yes. Since you have one correlation found as 0, your calculation would be little easier. Charit, Uresha,
34.713.
how much?
34.713.
I can't hear you. What is the first numbers? 15?
So the formula comes with the final answer was 34.71.
34.71. No.
So
Is that 48 point?
Huh? 1?
48.11?
No. Anyway, now what we need to do is, now there will be three square numbers at the beginning, right? So that is 10 squared plus 20 squared plus 15 squared, right? That is those are the three first terms, first three terms. Then you get minus, sorry, plus. Okay. I think you might be correct. You might be correct because there are no minuses here, no. So therefore, now someone said that it is 30 something, no, 34 points or something, no. Who said that?
34.71.
34.71. That may be correct. Yes. Wait. Yes, the 34.71. That answer is correct. That answer is correct. So I don't think that you need any blackboard demonstrations for that, because I will just tell you the way it has to be done. The ULA squared is 10 squared, that is 100, plus ULB squared is 20 squared, that is 400, plus ULC squared is 225, 15 squared, 225. Then you have to have 100 plus 400 plus 225 plus 2 row AB. Row AB is 0, so therefore that particular term doesn't come. It is 0. Then you get 2 row BC, that is 2 into 0.5 into 20 into 50. Again plus 2 into 0.6 into 10 into 50. And altogether it would come as 1200 something, and the square root of that would be 34.71. Mativadani has got the answer, and all others can try and see what is happening. And what I want to tell you is, now we have to analyze or discuss the answer. Now answer you got is 34.71. Okay, 34.71. Now you can see what has really happened. Now the particular loss is higher than any of the portfolio individual loans, right? Now all the individual loans, what is the highest loan? Individual loan 15 million. Sorry, 20 million is the highest loss of the loan, one of the loans. But the portfolio loss has go up, that is 34, but it is less than the total. Now if you take the just total of it, 10 plus 20 is 30, 30 plus 14 is 45. Now even though the unexpected loss total 45, but our portfolio unexpected loss we got as 34.71. So that is less than 45. But anyway, it is a bigger amount. The portfolio loss is a bigger amount. Now it would have been more bigger if you got a row AB, a figure, a positive figure. If you have got a figure, but luckily we have not got a figure for that, that's only 0. But if you got 0.5 or something there, the portfolio loss would have been bigger. I think you got my explanation. Is that okay? Any confusion on that? Any confusion? Right. Now, you can see even with a certain difficulty, we will be in a position to calculate the whatever the number you have in a portfolio. You should be in a position to calculate the portfolio unexpected loss, provided that you know all the correlations. Provided you know all the correlations, right? If all the correlations are zero, what will happen? Yes, I'm just asking a question. Right. I will give you a sum. Right. Now there's a question here. There are 4 loans A, B, C, and D in the portfolio. ULA is 10 million, ULB is 15 million, ULC is 5 million, and ULD is 8 million. If the portfolio is 100% diversified, what is the portfolio unexpected loss? It is 100% diversified. What does that mean? What does that mean? Yeah. When you say 100% diversified, what is the meaning? There's no correlation at all. Right? Then do the calculation and see what it is. Now, since you have four assets, how many correlations would be there or expected? 6 correlations expected, is it? But all these 6 correlations would be what? It would become 0 because since it is a diversified portfolio, no correlation at all. Is that okay?
So what are the 4 figures? 10, 15, 5 and
15, 5 and 8. The last one is 8. Now, this is a situation where all the loans in the portfolio do not have any relation, any correlation.
20.34.
Yes, you can just put the answer on the panel. In the panel, you can put it. $20.34. Yes, we'll see. Yes, your answer is correct. 20.34. So what we have done was, since the portfolio is 100% diversified, the meaning is there's no correlation at all. Then all the loans are independent. Then when you apply the formula, all the correlation terms will become zero. Then you can, the remaining figures only, there are four square figures. That is the 10 squared plus 15 squared plus 5 squared plus 8 squared. And you have to get the total of those squares and get the square root. The total of the squares would come as 414. Then the answer would be, square root of 414 would be 20.34. So that is how the answer is taken. And you can see, since it is a diversified portfolio, comparatively, the portfolio loss is low. Comparatively low, 20 point something only. So that is a small amount higher than the largest loan. So largest unexpected loss is from loan B, that is only 15, whereas the total loss would be only 20.34. So that happens since the loans do not have the correlation. I think now you got some idea here without much issues. We can go to the presentation again. Now, I think you people can join one by one into this, and I am happy that now some people are joining than last time. I expect all of you to join, right? You all join lively here, then you will get the benefit, not me. So you all can get the benefits. And just think that these things are not that difficult. You only have a fear. So you can just get rid of that fear by doing these things. And I can help you in that. So make sure that you get the best out of these lectures. And at least you can enhance your confidence. That's very much advantages in your careers. Because now we are facing a very challenging situation in the country. So all of you should try your best to develop your competencies. Then you can just get rid of all these downturns or whatever. Right. Right. Now you can see these things here. And if you go to the effect of correlation, right. Now we will go to this. Now, unlike in that formula, we have given a certain other type of thing here. Now, just again go to the copulas. Now, this copula thing is a new innovation. Now, here it is discussing about the unexpected loss of a certain asset or certain loan that is equal to now when you say AI is the correlation between two assets, F is the common systematic risk factor, and ZI is the idiosyncratic factor for ith asset. Now, we can go into another analytical method in a credit portfolio risk assessment. And there's a model called Vasisek Model. And this model provides an easily implemented way to derive the default PDF of a portfolio given the correlation between assets and the expected default rate. Now, expected default rate in the sense that is the individual loans default rate, but we are trying to get the portfolio default. Now you can just look at this formula. Look at the formula. That formula gives, now when you say N, that is the normal curve or normal curve scores that can be taken from a normal curve. You know, there's a particular table given in books, standard normal curve areas under the normal curve. So that is a chart you can find in one of your books. I will just provide that for you at a later stage. Now in the Vasisek model, the things are given in this nature. Now rho is the general correlation between the loans in a particular portfolio, but here it is assumed that for each and every loan, the same correlation prevails. Right, the things are described here. I will just put you through an example, then you will be in a position to understand this. Now this is the model. PD is equal to N within brackets N to the power minus N EDR plus square root of rho into N inverse 1 into theta PD divided by square root of 1 minus rho. Now those things all are symbolic expressions, so you need to understand what these things are. Now we will go through this, where rho is the asset correlation parameter. Theta PD is the cumulative probability function for EDR. Now just look at the formula, and we call this Vasisek model. PD is equal to, now the PD here, the PD means the portfolio probability of default. We are talking about a portfolio. Portfolio probability of default is the PD. Then you have other terms here. Just expect to get the other terms. EDR. EDR is the expected default rate. Now, expected default rate of the portfolio loans. Then rho is the correlation between each loan. And here the assumption is all the loans have the same correlation. All the loans have the same correlation. So that is the assumption. So we have to make sure that that assumption is there. What is that assumption? Now you can remember that when we talk in terms of several assets in a portfolio, there can be number of correlations. But in this type of portfolio, in the Vasisek model portfolio, we assume that all the loans in the portfolio are with similar correlation. So that is taken as rho. That is taken as rho. So then there's another one called another function. We call it theta. The Y type letter. It is theta. Theta PD is the cumulative probability function of the probability of default. Right. Now we will see how we can use this in a calculation or quantification. Now you just look at it. Where rho is the asset correlation parameter, theta PD is the cumulative probability function for EDR. Right. Now we will see. To see how this works, assume that rho is set at 15%. Rho is the correlation between two loans in the portfolio. Every loan has the same correlation, and that is 15%. And the PD of the portfolio is also 15%. So that is EDR. If theta PD is equal to 10%, the value of PD is then 4.82%. Now we can see how this calculation has been done. Right. Now, in order to do these calculations, you need to have normal curve tables. Normal curve tables. And those tables I will provide you with the help of IBSL. Now, even if you look at some textbook, at the end of the textbook, these normal curve tables are available. But anyway, if you can just go through that. So I will, during the break, I will ask IBSL to just send that normal curve tables to your online class, right? So then we will start again by 10:40. You can have a break now. Okay. We will start the session again. And I think you have already now noted down the Vasisek model formula. Now we will see how we can apply the formula into the day-to-day activities. Now, as per the assumptions, now we assume that the particular portfolio we have taken into consideration has a correlation, general correlation everywhere. I mean, every loan, the correlation is similar. It is 15%. And the EDR, expected default frequency of the portfolio, is also 15%. Then we have assumed also that theta PD, that is the EDR's cumulative frequency distribution, is also 10%. Then our task is to calculate the value of PD. So you can just look at it. Now you just see the n and n minus 1. Now when you say n to the power minus 1, that means it is what you call inverse normal values. What do you mean by inverse normal values? Now when these values being taken as percentages or the probabilities, what is the Z value? So that is what you mean by n to the power minus 1. So I will show you how to arrive at the number. Now, making use of the normal curve table, we can just do the calculations. Just look at the normal curve table. Are you ready with the demonstration? Are you ready with the demonstration? Yes. Are you ready with the demonstration? Yes. Yes, Charik. Are you ready? Because now you have to be vigilantly follow this. Otherwise, it is little difficult for you to just get it. So I request all of you to be vigilant with the presentation, because this is a very important lesson unit. Because you right. Now we can go to the presentation again. Now when you say, now with these values we are now putting, or we are substituting into the formula. Now when you say the EDR, expected default frequency, even though this is given as PD, it is expected default frequency. Now this is 15%. So then we can put in place of this as 0.15. And even the rho is also 15%. So that is square root of 0.15. N to the power minus 1. Again, this cumulative frequency is also 0.10. And that is how the things been given here. Then, so now then we can read it. We can read this. Right. Now, what do you mean by n to the power minus 1.15? So, I will show what it is. Are you with me? Yes, are you with me? Yes, Suresha?
Yes, sir.
Right, okay. Because the thing is now, this is a little critical type of a thing where I want to demonstrate. So, you all have to be vigilant, right? Now, when you go to the standard normal curve table, we want to see what is the inverse normal value for 0.15. Now, just look at the table. You have to see, right, in this table. Now, I can just show you the arrow here, because we need to check where is 0.15. But only issue is you can't have a similar thing here, but there's a closed one we can have. Now, just look at it. Now, you have 1.15151, and at the same time you have 0.14917. But this is little lower than what you want to see. You want to see 0.15, no? But this is not 0.15. This is 0.14917. This is 0.15151. So how can you get the answer? But you can see this particular line, it represents minus 1. This is the search score for that. Minus 1.0. But when you take this, what is this? It is 0.3. Here, 0.3. Then minus 1.03 is the answer if you take it as 0.1515 something. But here is the place. Now, this is not the answer, but the answer should come in between this one and this one. Is it clear? Yeah. But it is, now what you can do is you can just look at these two places. If you take this, the value is little lower than what we want to get. If you take this, the value is little higher than what we want to get. So then what we need to do is we have to have a value in between somewhere here. So then the corresponding value also we have to get. So what are we going to do now? So it is like this. Now just look at this. Now you have 0.14917. Then you have 0.15151. Then minus 0.14917. Now there you have 0.00234. But what we need to do is we need to get the difference. The difference is 0.00151. So out of this, what is the percentage we can see? Then what we can do is 0.00151 divided by 0.00234. 0.645. So that means 0.036. Now we can see the value would be then minus 1.036. 036. somewhere here. You just look at the arrow. It should be somewhere here. 0.0364, like 0.0364. So that is how the point being calculated. Right. So now the value has come here this way. Is that okay? The determination of Z values through the normal table. I have now explained.
So can you repeat again after this difference is taken? How this?
Yeah. That's the thing. Now I will go again. Yes. Now our value is 0.15. Whereas in the table you find only 0.15151. Here. Here, this is the one value we. Then there's another value here. It is also close to that, but it is lower than that. Then what we can do is we can see what is the amount we need to add, because now that difference is 0.00234. Now if you take the difference between 0.15151 and the 0.14917, the difference is 0.00234, right? Now what is the additional amount here? Now we need to get 0.15, but here you have 0.15151. So what is the additional thing here? What is the difference here? The difference is 0.00151. Is that okay?
Yes.
0.00151 has been added, no, to 0.15 here. So then that is, now we have to see what the portion of 151 is. Now say, when you go to the next one, what is the difference? This is 0.03, this is 0.04. There's a 0.01 difference in between these two things, no? But we have to see 151 represents what percentage of difference. So when you calculate that, you will get, now the calculation is done this way. Since the difference here is 0.00151, right? 0.00151, the total difference is 0.00234. We have to divide that by 0.00234. When you do that, you will get a value 0.645. 0.645. So therefore, what we can do is, this can be taken as minus 1.0364. 1.0364. That is how it has been calculated. If you want, I can put it on the board and you just explain. So this is a very simple thing, but even in standard 10, this type of things we do. Anti-logarithms and logarithms you do know. So the same way you do it. Is that okay? Yes. What do you say? Now you can see the corresponding Z value minus 1.0, but the additional things we have to take from this column, right? The column you can take, the column is 0.03 column, but it is not exactly the 0.03 column. It is somewhere here. Somewhere here. So that is what we check. And it is taken as 1.0364. Is that okay? Yes. Is that okay? Yes, Urisha.
So doing the calculation, that means the 0.00151 has to divide it by 0.00234.
Yes. So after dividing, you get a value 0.645 or something, no? You got that value 0.645. Then that particular value is the percentage difference, right? So then now
Yes.
what we can do is 0.03 is there, no?
Yes.
0.0364. That is the way you can take it.
Okay. Right, sir. Thank you.
So then we can just find out the value. Right. Now it is minus 1.036. I have put it as 06 because since the other decimal is 4, no? So therefore I just put it as 1.036. Okay. Then square root of 0.15 is taken as 0.387. That is correct, no? Then again you get another value n to the power minus 1.10. Now can you just check that? Now you have the value, you have this standard normal curve in. Now here you have to check 0.10. 0.10. Just show me where's 0.10. Now it's here. 0.10 is here. 10027. But it is not exactly the 0.10. But there also you have to go little away from this. But the difference is only 0.0027. Then you have to see the difference between this and this. What is that? 0.10027 minus 0.09853. You get a value 0.00174. 0.00174. So then what you have to do is you have to divide 0.00027 by this one. Point 0.00027 by 0.00174. That comes as 0.155. So 0.155 means minus 1.0 0.85 like or 0.9 0.85 or 0.85 or 0.86 1.086. Anyway, we will see what it is. Yes, it is 2 minus 1.2. Yes, 1.28. Yes, 1.28. 305, 1.285, I think. 283 should be 285. Is that okay? The next one. Now next one is 0.10. You have to get the minus or the reverse of reverse normal of 0.10. So it comes to this 0.10. Here it is here. So if you take the line here, yeah, This is the line. Then you start with minus 1.2, then you have to be here. It is minus 1.28 then. 1.28 or 0.8, 1.28. Then the next decimal we have to find, because you have a difference of 0.00027 here, and the total difference is 0.00174 something. So then you get 0.55 something. Then it is minus 1.285 or something, 285. But I think there it is given as minus 1.283 or something, no? It is given that way. Yes. Then in the denominator you have square root of 1 minus 0.15, that is square root of 0.85. That comes to 0.92195. So that is 0.9220. Yes, it's correct. Right now, after doing the calculations, you get within the brackets, the value would be minus 1.66. Minus 1.66. That is the value coming in the within the brackets. So then we have to get the probability for this Z score. That is what you mean by n minus 1.66. So you have to just go to the tables again and just go for minus 1.66. 1.6. Now 1.6 is here. 6 would be somewhere here. Somewhere here. Yes, 484. 46 is 485. It should be 485. Is that okay? Then the PD is calculated as 4.85.
Sir, in the question it says PD of the portfolio is also 15%, but we also arrive at a PD of 4.8.
Yeah. There's a small type of a confusion. But what you need to say is PD of the portfolio is, I think the word PD should not be used there. It should be EDR.
Okay.
EDR of the portfolio. I think that's a good point to note, because you just, it is not that correct to say that it is the PD of the portfolio, because we are going to find out that no, the PD, it is not the PD, it is the EDR of the portfolio.
That means expected return of the portfolio.
Yeah, expected default frequency. That is not the PD.
EDR, sir. Oh,
EDR.
EDR. Okay,
Yes,
okay.
EDR.
Default.
No, I think this you have to change. I mean, rather than PD, it should be EDR. Right. Anything else you need to clarify there? Because I think this is not a very straightforward one. There have been several assumptions, several notations, several types of statistical gimmicks or whatever. so therefore, I think you need to make an attempt to understand this, and this can be helpful for our analysis. That is what I need to tell you. This is very much helpful in our analysis, especially the portfolio analysis. Now, I just want to have a small discussion on this. What is the real implication or real applications of these things? Now, for example, if you have a portfolio, what happens is if the portfolio is a homogeneous one. What do you mean by homogeneous? Now, say in most of your banks or your organizations, you deal with different types of loans. Now, for example, if you have a SME type of advances in one portfolio, those advances more or less have similar characteristics. And such advances are called homogeneous type of advances. And that's a homogeneous portfolio. So SME portfolio can be considered as a homogeneous portfolio. If you take the housing loan portfolio, that also could be considered as a homogeneous portfolio. The homogeneous means it has similar characteristics. Each loan has similar characteristics. So that there we have another assumption little forward. And that assumption is in such a portfolio, you have a correlation with each loan. The correlation is more or less similar. There can be a small difference, but as a whole, you can consider it as similar. So that is denoted as rho. And we call it the portfolio correlation. And there would be expected default rate also in the portfolio. But that expected default rate is not the portfolio default rate. It is individual loans default rate in the portfolio. So all the loans are having the same EDR then in that case. And that EDR is distributed in a normal distribution. That is what it means. Then again, we go to another function, we call it zeta PD. That is the function, the probability of defaults being cumulatively distributed. So again, we can see the explanation. Now, sigma PD is the cumulative probability function for EDR. Now, EDR is, we have taken EDR here, and sigma PD is the EDR's cumulative function. So that EDR's cumulative function is very much close to PD. So that is denoted as zeta. Now, this particular, just like a threshold, we call it zeta, Z, double ETA, zeta. Theta PD. Right. Now, this is what you call the Vasisek model. Now, this is the example for that, what we have done. Anyway, we will have a small example for this again. Then otherwise now you might, sometimes you might get confused with the things. Shall we have a practical type of example? Right, I will just put you a certain example on the board. Right, now we have an example. I will read the thing for you. A portfolio with 100 loans has recorded an EDR of 12% for the last 10 years. EDR is 10%. All the loans have a similar correlation of 20%. If the cumulative probability of EDR is 9%, calculate the portfolio PD. So what you can do is you can make use of the Vasisek model. You can do the calculations.
So can you repeat the question, please?
Yeah. A portfolio with 100 loans has recorded an EDR of 12% for the last 10 years. EDR is the expected default rate. All the loans have a similar correlation of 20%. 20% is the correlation with each loan. If the cumulative probability of EDR is 9%, calculate the portfolio PD. Now you have that Vasisek model equation. PD is equal to n of n to the power minus EDR plus rho into that type of formula. Now the formula is with you. Now I will show the formula for you again. This is the formula. This is the formula. You can see this, no? Right, now you can place the things here. So then what should you write here? EDR n to the power minus 1 within brackets. You have to say what is the figure you put here. Now, since the loan portfolio is a homogeneous one only, you can follow this. Otherwise, you can't. So, what is EDR here? EDR is given in the sum. That is 0.12 n to the power minus 1, and within brackets you can say 0.12. Then plus square root of rho into n to the power minus 1. What is theta PD? That is the cumulative probability function. What is the percentage there? 9%. So you can say n to the power minus 1, 0.09. 0.09. So in the denominator you get 1 minus, what is rho? Rho is 20%. 0.20. 1 minus 0.20 is square root of 0.80. In the numerator you get square root of 0.20. Is that okay? Can you try to do the calculation? Can you try to do the calculation? Yes. Yes, Resha?
So, sir, just one clarification.
Yeah.
This says a portfolio with 100 loan has recorded an EDR of 12%.
Yeah.
So then we do have another, if cumulative EDR is 9%, so we get it onto this second part. So practically, what is the difference on this two EDR?
Yeah, the cumulative means, now say for example, you have if you take loans separately, if you have the loans separately, the separate loans will have a EDR of certain amount. So that is what you call that 12%. Okay, 12% is that. But when you take the cumulative thing, cumulative in the sense now, when you take the loans as a total, so then you call it a cumulative frequency.
So the first one is as a general for the portfolio is calculated, and second one
general in the sense that is for each loan.
Okay.
For each one. Now you have to take it singly. It's a single loan. Single loans EDR is that. And we assume all the loans are having similar type of EDR in one go.
Okay.
But when you take it as a cumulative thing, cumulative in the sense now you take all the loans together. If that is the case, the cumulative frequencies, cumulative EDR would be 9%. That is what it says.
Okay.
It's a function like. The accumulation means now when you take the loans together. So you get that particular probability. So that is what it means. I think that question is a valid question, because otherwise you might get a confusion, because you are doing the same thing again and again. Is that the doubt you had?
Yes, sir, because the first sentence it said the portfolio generally,
Yeah, of course.
portfolio EDR cannot be changed. It cannot
Of
have
course.
two
Yes.
numbers.
Yeah. No, the meaning here is 100 loans has recorded an EDR of 12% for the last 10 years. And EDR means expected default frequency for each loan in a single way, one by one. If you take one by one, the EDR is there. But if you take it as a whole, I mean, accumulation, it is not the PD of the portfolio itself, but it is a cumulative function for the EDR. Cumulative, we call it cumulative probability function, right? Now I think the matter here is you are not very conversant with these cumulative probability functions, no? That is the issue. So when you say cumulative probability function, it expects to have cumulative effects in one by one. The loans, if you take, say, since that is why I have given the number here. There are 100 loans in the portfolio. And these 100 loans will have separate effect if you take the cumulative distribution function. So that is why the cumulative distribution functions EDR is different from individual EDR. You got my point?
Yes, sir.
Right. So then that particular demarcation only you need to take into consideration. Now, when you talk in terms of cumulative distribution function, it's a different case. But when you say EDR is the individual loans probability of default. EDR is that. Expected default rate. That is what it means. Expected default rate. So there what we do is we just do the expected default rate as a distribution. But that distribution applies to each loan. Each loan it applies. You got my point? But when you have the other one, the cumulative thing, it applies to the total of it on the EDR basis. The basis is EDR. EDR is cumulated there, not the probability of default of the portfolio. It's a different measure. Is that has it cleared your doubts?
Yes, sir.
Right. So anyway, I think it may not be the total clearance would not be there, but I can just say that is the reason we put it in that manner. But I think if you need more clarification, actually the thing is you need to understand the difference between probability function, probability distribution, and a cumulative probability distribution. So that is the difference. That is the demarcation here. In one side, you have a probability function or probability distribution in one side. The other side, you have cumulative probability distribution. That is the difference. I will put it on the board like now. Say, I am really appreciating your query, because that is a normal or normal type of a confusion a person get at this point of time. Probability distribution. Now, this is what you refer to EDR, right? When you say theta PD, it's a cumulative probability distribution. Even though you put PD here, we should put EDR rather than PD. So if that is the case, it would be more more understandable. Just look at it. Probability distribution. EDR is only a probability distribution. Theta EDR or theta PD is a cumulative probability distribution. That is the difference. That is the difference. Now I think you have got it. So we demarcated in that manner. Is that okay?
Sir.
Purisha?
Yes, sir.
Right. Now we will go to the question again. Shall we do it on the board, the question? Or have you tried? Or have you attempted to do it? You have to use the same Vasisek model there. N within brackets n to the power minus EDR plus square root of rho into theta PD divided by square root of 1 minus rho. So that is what you normally consider as the Vasisek model. Because even though this looks like little difficult, but I think if you try it on your own, you will find that it is not that difficult.
Sir, can you do it in the board? Then we can check the processes that we are following are correct.
There was a small issue with the network, I think. Anyway, now it's okay, no? Are you getting me?
Yes, sir. Can you do it in the board? Then we can check.
Okay,
whether we
I
are
will.
following the
Yeah, I will do it. I will do it. Right. ED is equal to, now this is the Vasisek model, n minus 1 EDR plus n minus 1, sorry, rho into n minus 1 theta PD divided by square root of 1 minus rho. Right, now this is the formula. PD is equal to n to the power minus 1, that is the reverse this thing, EDR plus rho n to the power minus 1 theta PD divided by square root of 1 minus rho. Now we will substitute the values there. N minus 1. What is EDR here? 12%. It is 12%. So therefore you can put it as 0.12 plus rho is 20%. So therefore it is 0.20 n minus 1. Sigma PD is the cumulative probability of EDR. It is 9%. So we can say 0.09. Right? Divided by square root of 1 minus rho. Rho is 0.20. Is that clear? Now this substitution, you have to be careful about this substitution. The substitution is EDR substituted with 0.12 because it is 12%. Theta PD is substituted with 0.09, that is 9%, and rho is 0.20. Those are the only substitutions. And later on, what we need to do is we have to get the inverse normal table figure for 0.12. 0.12. Can you check and see what it is as an exercise? And here also you have to get 0.09's normal Z score, whatever, the reverse normal table thing. Just do it. Now you can use the normal table. Can you see the normal table? Yes.
Yes, we can.
Right. Now in the normal table, now you just get the inverse score for 0.12. 0.12. Can you can you just look at it and see where it comes? 0.12. 0.12. Just look at here. Yeah, somewhere here. 0.12100 is there. I see. Is it? So can you arrive at the score for that? But we need to get 0.12, not 0.12100. But we can have a method of calculation for that. So you can see that in that particular row, the score is minus 1.1. But corresponding with this, what is the real score here? So just arrive at that score. Yes, Suresha, you can just see how you can arrive at the figure here. And if you arrive at a certain figure, just let me know so you can put it on the message table.
Do so.
Try to put your answer for that. I'm just asking to get the inverse normal curve value for 0.12. 0.12. You have found 0.12100 and 0.11900. So in between you get this value. Minus 1.1. Yes. It's not that difficult. You can message it, the answer. Now our figure is 0.12, no? Since our figure is 0.12, you have to just look at the figure which is very close to that. Now you have a higher one, 0.12100. And there's a little lower one, that is 0.1199900. Now you can see the difference between these two. You get 0.002 as the difference. 0.002 as the difference. And what is the difference of this particular figure with our required figure? Our required figure is 0.12. This 0.12100. So there the difference is 0.00100. And it has to be divided with 0.002. Then what is the percentage there? That percentage has to be added here to this particular number, 0.1 minus 1.17 something. So that is what you need to do. Just do it. Yes. Yes, Suresha. Charit?
Yes, it is 5%, so we have to add
Yeah.
that.
Yeah. Then you have to say 1 point minus 1.175, is it? Because it is in the column 7, no? The earlier one? Column 7 or column 6?
Yes.
Column 7, and then you have to have adding up 50% of the other thing, no? So 50% means you have to put 75. Minus 1.175. Is that okay with you? Minus 1.175. Is it okay? Now just look at the table. Now, these are the points you need to look at. Right, this is the row, no? This is the row. In this row, now our attention goes to these two figures, because this figure lies on column number 7, is it? 0, 7, no? Column number 7. So we can say minus 1.17, but it is not the case because it is exactly not the same. But there's a difference of 0.00100. So that difference will be somewhere here. So then that difference is 50% of the particular gap. So 50% means 5. So then we have to say minus 1.175. So that is how this normal score is defined. Minus 1.175. I think, are you okay with that? That's what I'm asking. Minus 1.175. Are you okay with that? Yes, Charit, Desha, Urisha, are you okay with that? The value for 1.17.
Yes, so only thing that's a 1.18 value is 0.119.
Yeah.
1.17 value is 0.12. So
Yeah.
if you go like if you want to take 1.12, doesn't it has to be a higher value?
No. You can just look at it. I think it goes the other way.
Okay.
It goes the other way. No, just look at it. Now it is reducing. No? When
Yes,
this
so-
is reducing, the value comes up. That is why we do it that way.
So that means we have to deduct this 0.5% from 1.18 practically. That means that 1.19 is the lesser value.
Yeah. Of course, yes. Deduct from that end. Yes, from that end if you do.
Yes.
But if you now inversely, what happens is now you have 1.1210 no 1004.7 no in the
Yes.
07 column, right? But when it goes down, the column goes up, is it?
Yes.
Column goes up. That is why it is like this. So now the reduction is 50%, no?
Yes.
Since the reduction is 50%, the column goes up by 50%. That is why it goes like that. So that is why we put it as 1.175.
Okay.
That all depends on the particular pattern in the table. Right. Anyway, I think now it's okay. Then the n to the power minus 0.12 is, we can just take the value as minus 1.175. Minus 1.175. Minus 1.175 plus 0.20 into 0.20 into that row has a square root or not? There's a square root. Now here there's a square root. And square root of 2 into n to the power minus 1, what is that? 0.09. Now can you go for the reverse normal value for 0.09? Just go for 0.09.
So this square root applies for both the values, no? Row and the...
No, row is in the other side. Row
Only-
doesn't,
only-
it doesn't apply. The row doesn't, row has to be taken separately.
Okay.
The n value applies only for that theta PD. So therefore, you have to get the reverse normal curve value for 0.09.
No, sir, the square root of both the values, so only the 0.2. That's not clear.
Yeah. Only the 0.2. The
Only
square
the
root comes
0.2.
only to the 0.2.
Okay, sir.
You can refer the formula again if you want. Here, in the formula you can see the square root applies only for the row, not for anything else. But in the denominator, whole 1 minus row, the square root applies for the whole 1 minus row. But in the numerator, the square root applies only for row. Right. Now you can just see where 0.09 lies. 09. Okay. Have you found the point? Because you need to check where 0.09 situated, where 0.09 lies. Have you found that? Just tell me the row number. What is the row number?
Minus 1.3.
Yes, minus 1.3. It is the row number, and you have two values, 0.09012 and 0.08851. So in between that, the value comes. Then it is, say, in the 0.03 column, I think. No, 0, 1, 2, 3, 4. 0.04 column, yes, that is minus 1.34, not 34. It is little further because you have 0.00012 additional value here. So that we have to see what is the percentage taken there and see the difference between, say, the particular gap, the gap with that is number 4.04, 0.04. Then yes, I think you have to come up with your answer. Minus 1.34. What is the additional figure? Yeah. There will be an additional figure. So the difference comes with 0.00161, and where you have this the difference from 0.09. The difference is 0.00012. 0.74 is the percentage, 7% like, and it can be taken as 0.7. So therefore it is, what is it? 0.7. Then the figure would be minus 1.3407. 1.3407. That is the figure. Is that okay? $1.3407, is it? Now can you put the value? So n to the power minus 0.09 comes as minus 1.3407, is it? 1.3407. Yes, 1.3407. Minus 1.3407. So I put it here, PB equals N minus 1.175 plus square root of 0.20 into minus 1.3407 divided by square root of 1 minus 0.020 is 0.80. Now this will be the value. Right. The upper expression you can just look at. Are you okay with the figures? Are you okay with the figures? Right, now we can do further simplification here. 0.20 as a square root, we can just check 0.20 square root. That comes to 0.4472. Square root of 0.8 is 0.8944. Now you need to get you would get a minus value here. Is that okay? Any confusion with the values? Yes. Yes, Jayasanka? Charit? Puresha? Now, are you okay with the values?
Yes, sir.
Right. So then we can do the further simplification. Have you done it?
So I got an answer of 1.939. I don't know.
1.939 is the
Last
final answer, final one.
Final one.
Final one. Wait. That is minus, no?
Yes.
Right. Okay. I will check. What is the answer? You got 1.984.
93.
93. Now you got these values. The first value was minus 1.175 plus
175 plus.
0.4472.
So I just got 447 only.
71. No, it's okay. No issue.
Okay.
Into minus 1.3407.
Yes, divided by square root of 0.8.
Yeah, square root of 0.8 comes as 0.8944.
8944.
Right. Okay. I think those figures are correct. Those figures are correct. Then when you do the other
Yes, sir. Then you get 1.9834.
Yeah, that's correct.
Minus.
0.189. Yes, that's correct. That's correct. I will do it again. 1.175 plus 0.4472 into 1.3407. So in the numerator you get 1.77456 divided by 0.8944. That comes to 1.984. 1.984. That is the answer. Minus 1.984 would be the answer. Minus 1.984. Is the answer. Now this is within n it comes. So you have to get the probability value for that. Minus 1.984. So how can you get that probability value? So just look at it. It is easier than getting the inverse value. So you go to the normal curve tables again. Minus 1.984. Minus 1.984. Right. 1.9 is here. 1.898 is here, somewhere here. Now this time what we do is we do the value for getting the value for Z score. That Z score we got is minus 1.984. So that is what you do here. Then you need to go to the row minus 1.9 row. So then 8 comes somewhere here. Yes, 8 comes somewhere here. 1.98 minus 1.98 is here. Now, in that particular column, you get the value as 0.02385. 0.02385 is the value there, but it is not the correct value because our value is minus 1.984. So then that is another 40% should be added. 40%. So what is that? Oh, so 40% should be deducted. 40% to be deducted because the next value is less than here, no? Less than this value. So it is to be deducted. So it's somewhere See what is that? 84. Then you have to have 40% of this particular gap. The gap is 0.02385 minus 0.023330. Yeah, you get a gap of 0.00055. So out of that, we have to have 40%. That is into 0.4. Yeah, you need to add 0.002 with the meaning. 0.000. Then it would be 7. No. 1 minus 1.984. Yeah. So this be deducted. 2 has to be deducted. Should be 2383 like. Six 2.02363 is the answer. So the answer would be, the probability would be 2.363. 2.363. So anyway, are you okay with that? Can you arrive at the probability figure? Probability? Can you arrive at the probability? So n of minus 1.984. Yes, what is the probability you get? Last, yes. Minus 1.3407. What is it? Here. Last 07. Okay. What you need is to just see how it comes, no?
Yes, sir.
Yeah.
Yes.
Okay, I will just go into that again. Just go to the normal curve. Can you see the normal curve on the board now? Yeah. Right. Now, what we needed was to get the 0.09's inverse normal figure, 0.09, right? Now look at it. Now we have to check 0.09 somewhere here in the table. 0.09 here. Now you just look at it. In this row, right? 0.09 is here, right? But it is not 0.09, it is 0.09012. And then next figure is 0.08851. So what we do is, we just see the difference between 0.09012 minus 0.08851. That comes to 0.00161, right? But our difference is what? our difference is only 0.00012, is it? So then we have to see it contributes, what is the percentage of contribution, right? So the contribution percentage is 0.00012 divided by 0.00161. That comes as 0.074. 0.074, right? Since it is 0.074, what happens is when you get the value as minus 1.3 and the corresponding figure here is 4, is it? Then you get minus 1.34. Then you have to add 0.74. Then you say minus 1.3407. 0.7 comes that way.
Okay, sir. Thank you, sir.
Right. I think we did that, and as the probability, when we check that, we need to get the normal curve or Z value for minus 1.984. Minus 1.984. So that is the next task we have to do. Yes. Minus 1.984. Now it is here. It is here. What is minus 1.98? It comes here. 98 here. But it is not minus 1.98. It is minus 1.984. So then the additional amount you have to deduct from here. So additional amount I took as 0.00022. 0.00022. So then what we need to do is we need to deduct 0.00022 from 0.02385. Then you get 0.02363. That is the value. 0.02363. So then the probability value comes as 2.363. The probability is 2.363. The PD is 2.363%. 2.363%. Right. Now we will go again to the presentation. Now rather more detailed one again we need to do. And we call it worst case default rate of a portfolio. Worst case default rate of a portfolio. What is that? What do you mean by worst case? In a very great type of economic downturn. So that is what you call a worst case default rate. We define WCDR. Now, when you say worst case, it has a timing and a confidence level. X percentile of the default rate distribution during a period of length T, worst case default rate. Vasisek model raised WCDR TX to the probability of default PD and a parameter rho describing credit correlation. Now, this X or we call it the confidence limit or confidence level. Now, if you are talking in terms of a particular period, say for a 1 year period, the worst case, I mean, at a 99.9 percentile, or in a confidence level of 99%, we can say the worst case would be this much. So that is what you mean by worst case default rate. And if you go to a particular example, you can get some idea about it. For an individual loan, if EAD is the exposure at default and LGD is the loss given default, the X percentile of the loss distribution is this much. Right. Anyway, we will see what is the meaning of this WCDR. Right. Now I want to just give you another concept, which we call the worst case loss of a portfolio. And sometimes we call it as value at risk. Value at risk. Worst case risk is always or also given as value at risk. What do you mean by that? Now the meaning is this. Now you are confident, 99% confident, the loss would not go higher than that. That is what you mean by a worst case loss. Or in other words, you can say in the worst scenario, what would be the maximum loss you are going to make? That is what it means. So then you need to give a certain possibility, or we call it a confidence level. We call it, say, for an example, when you say a 99% confidence level, the meaning is you are 99% sure that your loss would not go beyond a certain amount. That amount is called the value at risk. But there's a 1% chance of having a higher loss than what you have expected. So that is the danger here. Now, when you say a particular point here, WCDR TX to the probability of default, PD, and parameter rho describing credit correlation. Now, there what happens is you are using the same Vasisek model to calculate the worst case default rate of a portfolio also. Now, in that case, you have to say what is the confidence level. You have to see what is the confidence level also. Here also we can go through an example. then you can just go into the cumulative function as this, cumulative probability as this, in a worst case. Right. Now, today we can just understand how the Vasisek model can be used in getting the worst case default rate of a portfolio. Worst case default rate of a portfolio during a period of time. Now, for example, say if you want to get an estimation of a portfolio and you expect that the portfolio would have a difficult time in time to come with the downturn in economy or whatever. So you just expect the particular time period as 2 years. Within 2 years, if the worst happens, what would be the default rate of that portfolio? So that is what you mean by worst case default rate. And for that, you need to give a confidence level also. So then, if that confidence level goes to 99.9, so the meaning is you are 99.9% sure that your default rate would be this. So then that percentage has to be applied to your Vasisek model's point where you applied theta PD. So we can just look at it and see what is really happening. Now, if you go for an individual loan also, you can just have that. For an individual loan, if EAD is the exposure at default and LGD is the loss given default, the X percentile of the loss distribution is this. If you have a large portfolio of end loans where each loan is a small part of the total portfolio, the X percentile of the loss distribution is approximately this. Right, anyway, since the things are a little complicated, what I try my best is to just give you a simple version of it. Now, I think up to now, the calculation of portfolio PD, is that okay? Do you have any issues or any confusions? Any clarifications also? So without asking questions, I don't think that you can gather these things. Because next concept is the worst case default rate of a portfolio. And there a small adjustment has to be made to the Vasisek model. The only thing is you need to change the theta or cumulative probability function to a certain level. That is the only thing we do. All others remain similar, remain same. Now, if you go for 1 year, the T becomes 1 year. If it is more than 1 year, then it should be adjusted as it is. Now we have, for a portfolio, we can just take it. And I think there's no big complication here. Only thing is you need to see what is really happening or what is really changing in the formula. Now you just look at the formula and you can have a comparison with the earlier formula. Now just look at it here. Now rho, square root of rho into n to the power minus 1 x you have here. Now this x is equal to this x. That is the worst case default rate confidence level. It's a probability. That x comes here. That x comes here. Normally what happens is when you give a worst case rate, our default confidence level would be 99%. So therefore, x is more or less 0.99. More or less 0.99. So if that is the case, you can do the other calculations by using 0.99 here. All others remain same. Then you can arrive at the worst case default rate of the portfolio. Now, for example, if we do a worst case default rate for the portfolio, what we have now talked about. So there you had a EDR of 12% and cumulative default of 9%. Only difference here is you are not going to change any other things. What you need to change is only the cumulative probability distribution or cumulative probability of the distribution. So that has to be changed. That has to be changed to 99%. Now we put it as 9%. No, it should be 99%. So therefore, there you should get 0.99 as the score there. So if you put 0.99 there, 0.99 there, then it is okay. I'll say. I will show you that. Right. Now I will try to explain you a terminology or a type of a concept called worst case default rate. Worst case default rate. Now, if you want to get the worst case default rate for this one, we have already discussed this now. The only thing is you need to change this cumulative frequency or cumulative distribution of probability. This one only changed. Now say the worst case default rate confidence level is taken as 99%. here it should be 0.99. 0.99, right? Then you have to just do the calculations by using 0.99 here. So I think that can be an exercise for you. Now you would find out the worst case default rate of the portfolio which we have now discussed. So only change what we need to make is, instead of 0.09 here, you have to put 0.99 here. So you do the needful and arrive at the worst case default rate of this portfolio. I think is that, have you understood it properly? Yes, Tirukumar?
Yes, sir.
Yeah. Anything if you need to clarify, you just do it now. So it is easy for you to clarify those things during the lecture.
Okay, sir.
Puresha?
So, on practical terms, when
Yeah.
we arrive on these probability ratios, how this risk department transform this into this credit, because finally these portfolios are handled by credit department at the branch level also.
Yeah. No, it is like this. Now, when you do these things, you have to be, you have to stick on to your historical figures. Historical figures in the sense, now basically most of the banks now have their own rating models. Now with the rating models, they have decided to have a certain rating for these loans. And if you go through the loans and see that what is the migration or whatever it is, so the PDs can be arrived at. Now, as per the rating, the relevant or corresponding PD is very much visible there. Because if you have a rating model, then you can have those values. So that is the practical situation of a branch or whatever. So through the rating model, you should be in a position to arrive at the PD of individual loans. But all those individual loans, if you take a portfolio, if you do a real survey, you will find that about 95% of the portfolio loans are in same rating category. So what does that mean? Their probability of default is also similar like. For such portfolios, you can make use of this Vasisek model. You got my point?
Yes, sir.
Because it's a type of a survey you need to do for a substantial period of time. Now, I don't know, in your banks, do you have rating models, internal rating models? Do you have now? To my knowledge, I think most of the banks have their own rating models now. Since they have rating models, they are in a position to create migration matrices, rating migration matrices, and through that, they are in a position to arrive at the PD of loans. How do they arrive? Because they rate the loans. And when the rating is there, there's a corresponding PD for the rating. Now, if you take a certain portfolio, all the loans in that portfolio comes to a particular rating. Most of the time. Say in a hypothetical manner, it is around 95% of the loans come into a one rating category. So that means all are taken into one probability of default, similar probability of default. So the same thing, same assumption, and the Vasisek model can be applied there. But this worst case scenario comes into that portfolio when we experience economic downturn. Then we can just apply it and see in a worst case what would happen. That is a necessity of, in practical terms, that is a necessity of doing a worst case default analysis. By having the present data, we would be in a position to do that. Okay. In practical terms, you have to do it that way. At least you need to have an internal rating model. Otherwise, it is not possible to do these things. What do you say? I mean, you have any internal rating models in your organization? Yes, Suresha?
So must be having, because our headquarters are handling all these things.
Okay.
Because there's a separate division anyway, that our rating has to be done separately, and private sector rating has to be done separately.
Yeah. And only thing is, unfortunately, the international rating agencies rate only a very, very few customers in the bank. And it's about, say, less than 10. A particular customer or particular counterparty took a rating from an international rating agency. Such customers are very few and far between. Very few. So therefore, invariably, the bank should have an internal rating model to deal with it. Otherwise, they can't do anything. They can't do any credit risk management if you don't have a credit rating model. Rating model is a must. At least an internal model. Right, okay. I think with that, we can wind off the class today. But anyway, anything else, if you need to clarify, then you can clarify that.